Okay, so this is going to be the notes on light and the basics of light and the structure of light. So light is created by vibrating electrons. And when these vibrating electrons vibrate, what happens is they create two different fields. They create an electric field, so an area of electric influence from a vibrating electron. And because the electron vibrates, it actually makes a perpendicular area called a magnetic field. So an electromagnetic wave has both an electric field and a magnetic field. Okay, and as you can see with this on this the illustration here, they vibrate perpendicular to each other. So the blue is the electron. So the vibrating electric field, so the vibrating area of influence that the electron has is the blue. And when an electron moves, that electric field then creates a magnetic field, which is the red. And the combination of those two are moving to the right. They make up what's called an electromagnetic wave. Light is an example of an electromagnetic wave. But again, it's all created by an excited electron that has an electric field and a magnetic field. So electrons, these vibrating electrons, when they move, when they are energetic, they release these little particles of light called photons. Okay, a photon is a particle of light. Up until now, we've been talking about that light can act as waves. Light has a wavelength, light has an amplitude, light has a frequency, but light also has a particle associated with it called the photon. And as we see here, so we have an initial collision, causes an electron to bump up to a higher energy level. Think back to chemistry. And eventually that electron is going to fall back to its original energy level. So when it goes back downward, it releases energy, and that released energy is a photon. Photons are little particles of light. The interesting thing about a photon is a particle that has no mass. So it is a particle of light that has no mass. As I showed you before, so we have light acting as a particle, but light can also act as a wave and does act as a wave. And the amplitude, the height of the wave, is how much energy it has. So the higher the amplitude, the higher the energy, just like in mechanical waves. And as we see here, we have the electric field and the magnetic field vibrating at 90 degrees from each other, and the wavelength is going across your screen. Okay, so the amplitude is the amount of energy. Okay, the wavelength is gonna be affected by how fast the electrons vibrate. The faster the electrons vibrate, the shorter the wavelength, the higher the frequency. Okay, as we talked about, there's a particle of light. There's the photon. There's also this thing called the wave model of light. So light can travel through space from one place to another as in a wave. Yes, and some of you may recognize the symbol. It's not necessarily just Pink Floyd, but this is a prism that shows that light entering here, and it bends like a wave. Waves bend. Waves bounce off things. Okay, so all that being said, light can then act as both a particle and a wave. And again, the particle is called a photon. Okay, it's the smallest unit of light. Often called the particle of light. The energy of the photon depends on its wavelength. So the higher the frequency, the more energy they have. Okay, and the energy of photon is proportional to its frequency. So the higher the frequency, the more energy that has. The higher the frequency, the more waves that are produced in a given amount of time, the more energy the wave has. It's actually inversely proportional to the wavelength. The shorter the waves, the higher the energy level, the higher the frequency. Okay, this is talking about photons. Photons are either absorbed, so the photons either come in and are absorbed by an electron, or they're released when the electron drops down an energy level. But again, it's all about the photons. photons being absorbed or emitted. And when we look at light, we look at typically the photons being emitted by something. So again, the dual nature of light, that light can act as a wave, like it can hit something and bend. Light acting as a wave in interference when light mixed together and it makes different colors. Light acting as a particle. It actually bounces off things like laser lights, like you've seen, that can hurt like people's eyes and stuff. That's light acting as a particle. Okay. Also, light acting as a particle is really how cameras make individual pictures. Okay. So light is part of something called the electromagnetic spectrum. It's a range of electromagnetic radiation. Okay. And here's the thing. Even though light's a portion of it, all of these parts of the electromagnetic spectrum travel at the same speed in a given material, in a given medium. So the speed of light is actually the speed of the electromagnetic radiation. And radio waves are the longest. Gamma rays are the shortest. Okay. And the frequency of each wave, the only difference is the frequency or the wavelength. Okay, radio have the longest wavelength, gamma rays have the shortest wavelength. And the frequency is how fast electrons vibrate. So for gamma rays that are really, 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 really small, 0.0000000000001 meter, they vibrate super quickly. These electrons that make these gamma rays are vibrating really, really quickly. Radio waves, not as much. They don't have to vibrate as quickly because they're not making as many waves. Okay, the speed of light in a vacuum is 3 times 10 to the 8th meters per second. 3,000,000,000,000 meters per second. Okay. All parts of the electromagnetic spectrum move through a vacuum at the same rate. That's as fast as they can go. Okay. And light and all types of electromagnetic radiation want to move in a straight line as quickly as they possibly can. And when things get in their way, it slows them down. Water, it gets slower. Solid materials, even slower yet. Okay, so the more dense the material is, it goes slower, which is the complete opposite of mechanical waves. Okay, so electromagnetic waves want to go fast. They want those waves, they want those photons going in a straight line as fast as they can, nothing in the way. When stuff gets in the way, it slows down. Okay, so again, all portions of the spectrum travel at the same speed in a given medium, and they all slow down when they hit a more dense medium, as shown in this diagram. Okay, that is the end of part 1. I would like you to do the dual nature of light investigation, please. If you have any questions, let me know, and we'll see you in class.